Imagine you are 12 years old, tasked with preparing tonight's dinner. You have your raw ingredients lined up on the counter: a bowl of harvested rice, a pitcher of tap water, and a jar of fresh curd. Look closely at that bowl of rice. Camouflaged among the white grains are tiny, hard pebbles and bits of husk, picked up straight from the farm. If you skip cleaning that rice and cook it as is, someone is going to bite down hard on one of those stones. It is a quick way to crack a tooth and ruin a meal. To cook safely, you have to pull those unwanted pieces out. But what exactly makes a bowl of rice and stones a mixture? And why is knowing how to separate the parts of a mixture a vital survival skill in our daily lives? To answer that, we have to look past the kitchen counter and zoom down into the microscopic building blocks of matter. First, we have the pure substance. A pure substance is a material made entirely of identical particles with uniform properties, like pure salt or pure sugar. Every single block behaves exactly the same way. But nature rarely keeps things pure. Usually, those uniform blocks are invaded by blocks of entirely different colors, shapes, and sizes. This jumbled combination of two or more different pure substances that simply coexist is called a mixture. That is your bowl of rice and stones, or a scoop of garden soil. Since almost everything we interact with in nature is a mixture, learning to identify these building blocks makes it possible to design tools that pull these ingredients apart. There is a common trap here. When you stir salt into a glass of water, the salt vanishes. It is easy to think the two ingredients have permanently fused into an entirely new chemical. But mixing is a physical process, not a chemical one. The white salt blocks and the blue water blocks mingle, but they do not change their identities. The salt is still salty, and the water is still wet. Sometimes mixtures are obvious. A heterogeneous mixture is a combination where the different components refuse to blend and remain visibly segregated. Think of oil poured into water, where the oil stubbornly floats in a distinct layer on top. Other times, they hide. A homogeneous mixture is a combination where the distinct components blend so evenly they appear invisible to the naked eye. The salt water looks perfectly clear, but zooming in reveals the distinct particles of salt and water are still sitting right next to each other. This gives us a massive advantage. Because the parts of a mixture are never permanently fused, we can always find a way to separate them again. Back in the kitchen, we separate these mixtures for three highly practical reasons. The first is to remove harmful contamination, like hand-picking those dangerous stones out of your raw rice. The second reason is to obtain pure substances. When you pour tap water through a filter, you are trapping tiny, floating impurities so you can safely drink the pure water that passes through. The third reason is to extract multiple useful materials from a single complex starting ingredient. Look at this wooden churner rapidly agitating a bowl of thick curd. By shaking the curd aggressively, the heavy liquid drops to the bottom, while the light, fluffy fat rises to the top. From one bowl of curd, you extract two useful ingredients: buttermilk and fresh butter. Every act of unmixing in the kitchen ultimately serves to protect our health, guarantee purity, or transform one starting ingredient into two distinct resources. So, how do you know which method to use? You use the specific physical properties of matter as the mechanics for pulling mixtures apart. First is the rule of size. If the components in your mixture are different sizes, you use a barrier with holes. In this wooden sieve, the coarse clumps of roots and dirt are trapped on top, while the fine, powdery soil easily falls through the mesh. Next is the rule of density. If your ingredients have drastically different weights, you let gravity and wind do the work. By tilting this bamboo tray, the farmer allows the wind to blow away the incredibly light husks, while the dense, heavy grains drop straight down into a clean pile. Then there is the rule of magnetism. If one component is a magnetic metal, you bring in a magnetic field. Watch this crane hover over a massive pile of trash. The electromagnet instantly snaps up the jagged scrap iron, leaving the plastics and wood completely untouched. Solving any separation problem simply requires identifying the one physical property that makes your ingredients behave differently. By applying these rules, our 12-year-old chef avoids disaster. The stones are hand-picked from the rice, the water is filtered pure, and the curd is churned into fresh butter. The meal is safe. You rely on these same scientific principles constantly. When you boil pasta and pour the pot into a colander, You are using the rule of size to trap the solid noodles while draining the liquid water. When you pick the green peas out of a serving of palau because you do not like the taste, you are using physical separation based on size and shape. You already know how to do this. Understanding the why and how behind unmixing transforms ordinary chores into active problem solving. But the kitchen only covers the basics. When we need to recover invisible, dissolved solids from a homogeneous mixture, like getting solid salt back out of completely clear water, we have to scale up our techniques. This coastal grid shows separation on an industrial scale. These shallow pans are filled with thousands of gallons of seawater. By exposing the water to the sun, the liquid evaporates into the sky, leaving tons of crystallized sea salt behind on the ground. From the salt on your table to the fuel in a rocket, unmixing is what makes raw materials usable. Stay curious, because next time we're tackling the tools of filtration, evaporation, and distillation.